Hi, welcome to a new IGCSE physics video. In this video, we'll try to explore a simulation activity which you can download the worksheet in the description of this video. So go and do it now, and you will see there will be 5 pages in total, which consists of 5 different setup of the experiment in this simulation. And this experiment obviously is something to do with motion graphs that you will learn in physics for mechanics. And for the simulation, you can go to the top and you can find the link here. And if you try to simply paste it to your browser, you will see this loading screen. So just to make sure that you have patience to wait for maybe about 10 seconds, then you'll be able to get this system work. You don't have to download anything beforehand, and it should work on any sort of device that you have. But I'll recommend you to use the desktop if possible. So this simulation is called the moving man, and what you can do is you can change his position or velocity and acceleration as well. However, I will want you to go to the chart and follow my instruction according to the worksheet. So please pause the video if you haven't done this simulation yet. Go and do it now first, and I'll explain the answers to you.
2,000 years later.
Alright, so I suppose you have finished all 5 experiments and also the questions together with that. And let me try to do the experiment as well and see whether or not you have the same answer as mine. So the first experiment is to set the velocity to be 2 meters per second, and we just have to draw the graphs. And so let's go to simulation. Here you can see velocity. You can key in 2 on your keyboard. Some of you maybe try to drag the arrow. Actually, you don't have to, because in that case it's hard to drag it to be 2 directly. So just key in 2 and then press a button. If you like to show the vector, I think that's fine too. So yeah, this is how it is. You can see the man is moving with a constant velocity because we don't change it anymore once we start the motion, and the position will get changed with a constant rate. The rate, of course, is the velocity itself. Acceleration was 0 all the time because velocity didn't change at all until you can see now the man hits the wall, and therefore he has to stop, and therefore there must be a spike of deceleration there, and then now you can see the velocity becomes 0. So let me try to copy these graphs onto our worksheet. When you try to copy it, you don't just draw the rough shape, right? Like this one. This is not good enough, because if you think about it, you have to pay attention to the time where it stopped, because the man was not at the middle, which is so-called the 0 marking, and up to the end, which is 10 meters. So actually, if you try to do a bit of simple calculation, or if you simply look at the graph, you know that this should be 5 seconds. So that means this blue line would increase, the position would increase all the way up to 5 here, so around this point. So you can draw a line that should be a straight line up to a point when the time is equal to 5 seconds, and after that it will just be a constant. Okay, I don't have a ruler, but if you have a ruler on your piece of paper, please make sure you use that, and this is a way that you can draw for position. As for velocity, it's much easier. You just have to find out 2, so roughly 1/3 between 0 and 6, and that will be the horizontal line you do from 0 seconds until 5 seconds. Okay, and afterwards again it is 0 because it stopped moving. As for the acceleration, you do the same, right? At the beginning and also throughout the whole motion, it was 0 because velocity didn't change at all. Only when it hit the wall, then it has to decelerate for a very short time. So there's a spike here, and then maintains 0 afterwards. So this is our result for the first experiment. Okay, so now we have to move on to describe each of these graphs with the wordings that we learned in the previous video. If you somehow haven't watched the previous video yet about what kind of wordings you can use for each different kind of graphs, I'll put the link in the description below. You can go and watch it first. Okay, so for position time graph is obviously a constant slope, right? So I'll put that constant, but then this slope is positive, so positive slope, right? Constant and positive slope. For the velocity time graph, you can see it just maintains at 2 as a horizontal line. So if you really want to describe the line, you can call it as literally horizontal line, but then more precisely I would rather say it remains constant at 2 meters per second, okay, throughout the whole time, or until 5 seconds and then become 0. So here I just focusing on 0 second and 5 second, by the way, so I don't describe what happened after 5 seconds because that's not really the motion anymore. For acceleration is more or less the same, so you can also put down horizontal lines which remains constant at 0 meter per second squared. Very simple for the first trial. Second trial, this one should be very simple and you can kind of predict the result because the only difference between 1 and 2 is now you have a negative velocity. So how about I just predict it? Yeah. So I would say this guy, because of negative, because just now it moved to right, so now with negative it should move to the left instead. But that's really just a preference of the program. So don't ask me why positive is going to the right. I don't know. Somehow whoever programmed this chose it. But then since we already know right side is positive, then right side must be negative. So in this case, I could guess up to also 5 seconds because this is also 10 meter of distance that you move. And so up to 5 seconds will be around here. Then this should be the rate. Again, it should be a very strict and constant value. I mean constant rate of change. And then it becomes 0 again because there's also a wall here. Same for velocity, it will be -2. I'm trying my best to do it on my screen. And then becomes 0 after it hit the wall. As for acceleration, it will be the same, but this time the spike would then be positive because this is how you can decelerate in the left direction. So let's go and try to check out if my prediction is correct. Okay, so I guess we have to clear it and then put down -2 and start. Oh, I have to reset the position as well, so maybe I reset -2 and yeah, hopefully this is how it looks like. Yeah, doing very well. Position as the constant negative rate, velocity to be maintained at -2, acceleration maintained at 0, and boom, here is the peak we find, alright, as a positive value. So I believe these are all the same. Oh, I make a mistake. Oh my god, I'm so bad. Here, yes, sorry, I make a very stupid mistake. It should maintain as -10, alright? If what I drew was correct, that would be stupid because that would mean the person would teleport back to 0 and that doesn't make sense at all, right? I'm so stupid. Okay, did I make a mistake in the previous picture? Actually, I did as well. Oh my god, I'm so stupid. I can't even copy the graph properly. Okay, I hope I won't make another mistake in this video at least. So for describing the position time graph, then what we can say is we can say constant negative slope, right? Because it's going downhill. As for velocity and acceleration time graph, it will be very similar to our experiment 1, which we can say it remain constant at the value of -2 meter per second, and same for the acceleration. So I'm not going to write again, 0 meter per second squared. Okay, so it asks you about the difference between result 1 and 2, and so basically is to say the position time graph is going to be positive versus the negative slope. And in terms of this, actually what it means is that it's moving to the right direction versus the left direction. Alright, so this is the idea of how the negative or positive value of the velocity will affect the motion. Okay, let's try experiment 3. We have to reset it first and then set the acceleration to 2 meters per second squared. So this time the velocity should be changing. So let's try it out. So reset all, and then we do 2. Yeah, 2. Yes, that's correct. So let's start. So we should anticipate velocity will be changed in a constant rate because now acceleration is being constant, and so velocity will change in a constant rate instead. As for position, you can see it's a curve, and that's very normal because velocity has been changing all the time, and therefore the slope of the position will be changing. So let's just copy this. So this time it takes about 3 point something, I think 3 point something second to reach. So we can set these as 2. I know it's a bit hard to say, and then just to ensure this time I won't make any mistake, I will look at the answer. Okay, alright, be careful that this is 0 and this should be positive 2. Alright, they are not the same horizontal line. As for velocity, obviously it reached about 6. I think it really takes about 3 seconds, but then I think a bit more than 3. So it hit about at this point, and then a straight line. Okay, I can draw better. A straight line, and then since this is a point where it hits the wall, then it will become 0 afterwards and stop moving. Okay, and same for the position. It starts from 0 and then it reached to 10 at the same time. So make sure when you try to draw the graph that these time are all synchronized, all right, on the same vertical axis. So for the position, what I would do is I'll draw a line that is a curve, obviously, like this. All right, and then wait, I should not be making the same mistake again. All right, it will be stopped at the wall, so 10 meters right there. Okay, so this time is really something that you have to apply with what you learned in the previous video. For position time graph, it is obviously increasing. So increase with what? With an increasing rate. So with an increasing rate. For velocity time graph, it will simply be a constant slope because you can see the slope is constant. So constant slope, but then we have to tell whether it's positive or negative, and this time obviously is positive. And for acceleration time graph, you can say it remains at 2 meters per second squared, remain constant, I should say. Okay, and this is a description again from 0 second to that particular moment when it hits the wall, so roughly about 3 point something second only. Okay, so that should be good enough. Next is experiment 4. This time again is to ask you to set the acceleration as 2 but negative. So I think this time you can do the prediction as well. So my prediction is assuming we also start from 0, and this time is negative 2, so that's why we should know it is going to the left and reaching at negative 10 at the end when you hit the wall. And so for acceleration, it would still be a maintaining negative 2 to about 3 point something. I actually don't know how much time it is. And then there should be a small spike until it reach to 0. Okay, and then for velocity, it starts from 0, and then at the same time, when you finish accelerating, then it will reach to about negative 6. Again, because we're moving to the left, and then afterwards it will become 0 because we have to stop there by the wall. And for position, it starts from 0, and then when you reach here it's negative 10. So again, the same time here. So this is something that you can do in when you draw a graph in the future as well. Since you already know these two are the known position, then you can think of the way to connect them. Of course, you should not be connecting with a straight line because you know the velocity is changing, and then by a bit of thinking, then you should know it should be a curve like this, and then maintain at 10 once again. So let's try to check if the simulation agree with our prediction. Okay, so -2 for acceleration, and yeah, I think it looks pretty good. So negative is not exactly 0, but -2, and then the velocity go to -6, and then boom, 0. For position, it's also a curve like this. Am I right? Yeah, a curve like this, and then maintain at -10. Good, good, good. So for description, then again, you have to think about, especially for position time graph, using the wordings that we talked about in the previous video. And this time is obviously decreasing. And you can see the decrease is getting steeper in terms of the slope. So it is decreasing with an increasing rate. As for velocity, it is just a constant slope if you look at the graph there. So constant slope, and this time it is a negative slope, so constant negative slope. For acceleration time graph, it will still again be remaining constant at -2 meter per second square. Alright, finally we reach to our final experiment trial, number 5. And you can see this one is slightly more complicated because you don't set only velocity and acceleration separately. You set both at the same time. So we have to set velocity as 5, acceleration to be -2, and we have to hit the simulation button. And before that, I would like to do a prediction, shall we? So if you somehow haven't done that, I'll prefer if you can make a prediction. That would be nice. So let me think. So we'll start at 5, +5. So this is a point where we know. We start at 0, so this is a point we know also. For acceleration, it will be -2 somewhere around here. And the thing is, since we have acceleration to be -2 and velocity to be positive, that means you are having the velocity to be decreasing like this, right, in the graph like this, but then you have to think about how much time it takes to decrease. So since we can apply the idea of A equals to V minus U over T that you learned earlier, or you can simply think that, hey, when it was 5 to start with, after 1 second, because of acceleration, then it should become what? 3 meters per second, and then after 1 more second, it will become 1 meter per second only. Alright, so these are all the velocity, meter per second. And then after 1 more second, then it will be -1 meter per second. Okay, so this is an idea that you could borrow. And so after 1 second, or after 2 seconds, how about that? Then we have only 1. So I think this is about 1. Alright, I wish the scale to be larger, but then I think it's a bit hard for me to do that when designing this worksheet. But then, okay, so this is up to +1, and then after 1 more second, so it should be 3 seconds, so about here, hopefully, it should be something like this. And in fact, this slope should be maintaining constant because acceleration is -2, right? And so the slope should just be -2 all the time until I don't know when it hits the wall. Yeah, I really don't know. And so for the acceleration, it would just be -2 always. I think that's something you will be able to guess. For the position time graph, it's probably the hardest because at the beginning, your slope you can observe from the value of the velocity, so you can say it should be very steep, but then it becomes 0 afterwards. So I'm thinking it's something like something like this, because it is actually reaching zero velocity, v equals to 0 here. So that means the slope should get to be level off, like 0, when you hit 3 seconds. So probably something like this. Again, I don't know how far it will reach unless I do some other calculation. And after that, it should be going down like this, I think. Yeah, I think that's my prediction. So let's try to see whether my prediction is correct. Okay, so let's check. Okay, make sure you have reset it, and velocity to be 5 positive, acceleration -2. So let's start. Okay, it looks good. You can see the red line velocity keep decreasing at a constant rate, and at a certain point you can see it start to go back. If you look at the guy just now, it went backward. So this is the same as how you can see in the position time graph. You can see it getting faster and faster because it's getting more and more negative. Okay, and yeah, I'm quite happy with our prediction here. And yeah, I think they do match. Right, of course I have to draw what happened after I hit the wall, but I think the most important thing is I can predict what happened beforehand. Yeah, I'm happy with this. Alright, so for the description and for the position time graph, it will be slightly trickier this time, because you probably would need to separate the graph into two because they are of different shape according to the 6 options that we learned from the previous video. And we should know the time for this because acceleration was once again -2, and we start from +5 for the velocity. And so this time, like how we predicted, it should be somewhat between after 2 seconds to 3 seconds, so it should be 2.5 seconds actually. Yeah, because after 1 second is 3, after 2 seconds is 1, and so after 2.5 seconds should be 0. Yeah, so this is a time where the velocity hits 0, and this is a point where you have that guy return to the left direction. So what you can say about it in the position time graph is I would specify the time stamp. So I would say for 0 second to 2.5 seconds, it is increasing, right? Increase, you can say the line or whatsoever, increase with a decreasing rate, right? Because it doesn't get as steep later on. If you look at this part and the beginning, at the beginning is more steep and later on become more gentle. So with decreasing rate. Okay, and that's what we have. Then for 2.5 seconds to the point where it stopped, actually I don't know. I think this is about 6.5 maybe. All right. Did they say anything? No, I can't actually check. I don't think I can check that. Yeah. So I'll just refer to the simulation. That's 6.5, let's say, to 6.5 seconds. Then it is decreasing. The position would decrease with an increasing rate. With increasing rates. Okay, so that's the position time graph. It's kind of tough actually, like if you try to describe that. For velocity, what it is it will be decreasing, obviously, with the constant rate. So you can say it has a constant negative slope. You can also add one more thing, that is at 2.5 seconds, because this is a point where velocity equals 0. Then we have a saying in physics. You can say that it is momentarily That means at that moment, momentarily at rest. Okay, for the velocity. And lastly, for acceleration, you can just say, like we usually say, remains constant at -2 meter per second square. For the last question, I think I basically answered already. When time equal to 2.5 seconds, what happened? So that is obviously when velocity becomes 0. So you can use the word, don't just write v equals 0, right? The words, right? Velocity becomes 0. And you can also say the man turned the direction to the left, right? Because this is the point of returning to the left. And yeah, I think that's all we can say about. Okay, so there you have it. Now you know how to draw the 3 graphs, including the position time graph, velocity time graphs, and acceleration time graphs. You also learn how to apply those wordings to describe different kind of shape in the graphs. And lastly, I wish you can also observe during the activity of this simulation, you observe the relationship between these 3 graphs in terms of their slope or maybe the area under the curve. And if you don't worry, we'll talk more about it in the next video. I hope you enjoy learning with me. I'll see you again next time. Bye.